Welcome to the podcast of the Consortium for History of Science, Technology, and Medicine. I'm Bob Akashrafi. Today we're speaking with Joe Martin. Joe is Assistant Professor of History at the University of Durham, and Joe's the author of Solid State Insurrection, How the Science of Substance Made American Physics Matter. Thank you for joining us, Joe.
Thanks for having me, Bubba.
You start your book by recounting a controversy about the Superconducting Supercollider that exposed some long-standing tensions in the physics community. What was the Superconducting Supercollider, and how did that controversy expose these long-standing tensions?
So the Superconducting Supercollider was a scientific instrument that was never built. It was a proposed particle accelerator that was supposed to be built in Texas, south of Dallas-Fort Worth. And the basic idea behind particle accelerators is you take small particles, usually elementary particles, you smash them together at very high speeds, and you watch what comes out. And by trying to understand the interactions that happen when you do that, you gain a greater understanding of the basic rules that govern matter and energy at the very smallest scales. The Superconducting Supercollider was a machine that came at the end of several decades of development of these types of instruments, where they got increasingly large in physical terms on the landscape and were accelerating these very small particles, electrons and protons, usually to higher and higher energies, with the goal of filling out this fundamental theory of the basic constituents of matter and energy that's called the Standard Model. It was controversial mostly because of the size to which it had grown and the resources it was therefore consuming. This was meant to be a project funded by the United States, and many in the scientific community, including in the physics community, were worried that this machine was consuming resources, the sort of money and support and facilities that the government was giving to science, that was not commensurate with the sort of payoff that could be expected from it in terms of both the intellectual outcomes and in terms of the practical technological spin-offs from the project.
If we step back to the beginnings of your story, how was American physics organized in the early 20th century?
When we think about the history of American physics, we often think about relatively recent periods of history after the Cold War, after nuclear weapons, for instance, were developed in World War II. And so we're accustomed to think of American physics as a world leader. In the early 20th century, this was very much not the case. Before the turn of the 20th century, the United States in general was something of a scientific backwater on the world stage, and this is especially so in the realm of physics. There were a very small number of physicists who would have had international reputations around this time. J. Willard Gibbs was one, Henry Rowland was another, Joseph Henry. But for the most part, physics was happening in Europe. That's where the big developments were made. And so the American physics community was small, and it was mostly constituted by people who were trained in Europe. If you wanted to get the very latest in physical developments, to train with the best people in the field, you had to go and study in Germany, you had to go and study in England, you had to go and study in Switzerland or Denmark. And so when we're talking about American physics in the early 20th century, we're talking about a relatively small group of people. The American Physical Society, which was the flagship organization representing American physicists, had only a few hundred members for the first several decades of the 20th century. Because going to Europe was almost a prerequisite for getting the sort of training you needed to make contributions that would be recognized at an international scale, the people who had influence in the community tended to be people who had done that, who had gotten fellowships, for instance, from the Rockefeller Foundation or from the Carnegie Foundation, to go and study in Zurich or study in Cambridge or study in Copenhagen and bring that knowledge back to the universities that were being founded and growing relatively rapidly around this time in the United States. As a result of that, the power structure in the American Physical Society was very much centered on this more abstract European way of thinking about what science was. So the American Physical Society had been founded at the turn of the 20th century by a number of physicists, including Henry Rowland, who was an extremely powerful acolyte of pure science. So the power structure of the American physics community was directed towards making sure that there was a space in American society for the pursuit of pure physical knowledge about the world. On the other hand, as physics began to grow, it grew largely into industrial areas. There began to be a market for physicists in industry in the first decades of the 20th century, increasingly so after World War I and in the interwar period. So you have this interesting bifurcation in the physics community where the powerful individuals, the people who are determining the direction of the discipline, are people who really think that what physics should be is the disinterested pursuit of abstract knowledge about the physical world that should be undertaken without any consideration about whether or not that knowledge is useful. On the other hand, many of the people who are trained as physicists in the United States, when that starts to be possible, are getting employment in industry, and they represent a growing constituency in the American physics community whose needs aren't necessarily represented by the power structure of organizations like the American Physical Society. So that sets up a tension in the community that has to be resolved as the century wears on.
And how do they address that as physics continues to grow during World War II and afterwards? What were the relationships between physicists in industry and in academia?
There was a great deal of tension between academic and industrial physicists through this period, this middle period of the 20th century, precisely because of this resentment that built up in the industrial community over whether or not their needs were being represented. They would interact, so academic physicists and industrial physicists would often interact at conferences, but not as much as you might expect, because if you work for an industrial corporation, it's difficult to get leave to go and travel to a conference. Your employer is not necessarily going to pay for you to do that. There were a few outposts like Bell Laboratories, which had a very large stable of physicists who enjoyed the sort of latitude and the sort of support that you might expect in an academic environment. But if you're working for another industrial organization outside Bell and perhaps GE and IBM, Westinghouse and one or two others, you could expect to be more constrained by the working rhythms of an industrial facility. Because industrial physicists and academic physicists didn't communicate sometimes as much as either group really hoped that they might, one of the goals of efforts that started around World War II to rethink how the discipline was organized were centered on creating more opportunities for those people to become engaged. And for the people on the industrial side of that divide, they tended to favor the creation of more institutional infrastructure that would cater to their needs. They saw the American Physical Society as this ivory tower institution that wasn't really attuned to what they were doing, that wasn't willing to be flexible to accommodate the constraints that they were under in their own jobs. And so they favored shaking things up a little bit and creating some different type of arrangement that would suit their needs better.
And how did the American Physical Society adapt to these demands from industrial physicists?
This is getting into the nitty-gritty of the institutional story a little bit. So the American Physical Society, by this time, is quite large. It has several thousand members at this point. And in 1931, there was a provision written into the Constitution that said the American Physical Society may form divisions. Some interest group that's interested in a particular topic of interest within physics can get together, and they can form a division of the Physical Society that's dedicated to that topic, whose goal will be to organize meetings and symposia and events within usually the annual meetings that the APS would host. No one had taken advantage of that really before the 1940s. And during World War II, as a number of physicists are starting to think about how to organize the discipline after the war, some of these interest groups started to agitate to take advantage of that provision. And many of those groups were groups of industrial physicists. It was really during World War II when physics was gaining prestige. It made a number of visible contributions to the war effort, and physicists realized that they were going to be more influential in American society after the war. And because of that, they started thinking very consciously about how to organize their field after the war to take advantage of this increased prestige that they expected to have. One of the ways they did that was to try to reshape some of their organizations. In particular, there were efforts to reshape the American Physical Society so that it could bring these groups that would be more influential after the war closer to the center of the affairs of the society so that they could influence it a little bit more than they had in the past. One of the great contributions that physicists made to the war was radar. You had laboratories in Cambridge, Massachusetts, in particular what was called the RAD Lab, the Radio Research Laboratory at MIT, that was very quickly developing radar systems that would be deployed sometimes in a matter of weeks in the European theater, in aircraft, on aircraft carriers. This played a central role in the way in which the war played out. Many of the people who were working on radar in the RAD Lab at MIT, for instance, were working in fields that had not traditionally been at the center of the American physics community. So one of the efforts after the war, even before the end of the war, towards the end of the war, as it was winding down and physicists are thinking, what are things going to look like in a couple of years? One of the efforts that came about was one to build some structures that would give these sorts of physicists who might otherwise go and become engineers, who would probably go out and get jobs in industry, to give them a home in the American Physical Society. And that led a number of groups to take advantage of this provision that had been written into the APS Constitution in 1931, allowing for divisions of the physical society. So there was a division of electron and ion optics, for instance, that was founded in order to cater to the needs of electron microscopists. There was a division of polymer physics that was founded in the mid-1940s. And there was a division of solid-state physics, which was established broadly to cater to the needs of industrial physicists, even though they didn't say that explicitly. There had been a number of efforts to found a division of industrial physics, but the APS Council had routinely shot these down, saying, no, industry is not a topic of physics, therefore it does not deserve to be represented with the division. So solid-state physics was established as sort of a dodge for this rationale for shooting down a division of industrial physics, with the rationale being most of the problems people in industry are working on have something to do with solids. They have to do with metals, or they have to do with semiconductors. And so the division of solid-state physics was proposed as one of these mechanisms that could bring academic and industrial researchers into conversation more than they had been previously.
How did the division of solid-state physics fare? Did it develop into a flourishing division? Did it provide a professional identity for its members, or did it flounder?
It grew very quickly by the standards of divisions at the time. By 1962, it was the largest division of the American Physical Society, and it has remained so since. There was some concern early on that it was getting a little bit too big for its own boots, actually. There was some politics concerning with independent actions it took to arrange meetings. The central governance of the APS was worried, more or less, that it was going off on its own and not being responsive to the needs of the central community. But aside from those worries, it was healthy and robust, and in fact did do quite a good job of attracting membership from the industrial researchers who were one of its primary constituencies.
So there was a post-war boom in physics, including, as you say, in solid-state physics. But later on, in the 1970s, things tightened up. And how did the physics community and its various divisions adapt to the tightening up of funding?
Yeah, the change in the funding landscape had a profound impact on the way that the American physics community was organized. After the war, it was, especially by today's standards, remarkably easy to get money. And it's sometimes shocking when you come across grant proposals in the archives, where a physicist or group of physicists will be asking, say, the Office of Naval Research for money on the order of several tens of thousands or even several hundred thousands of dollars. And it will be a paragraph long. It will say, here's what we want to do. Can we have this amount for it? It was extraordinarily easy to get research funding in certain areas of science, most of physics being among those in the area immediately after World War II. Beginning really in the mid-60s, but certainly by the time the 70s rolled around, that had tightened up considerably. So you have the Mansfield Amendments in 1972 that essentially they strongly discouraged, let's say, the military organizations from funding research that wasn't directly relevant to defense. Now, you can stretch the bounds of what counts as directly relevant to defense quite a bit. But at the same time, that still narrowed the range of funding that was available to much physics research. And this tightening of resources produced more or less what you'd expect to happen, which is more competition among the various subgroups of physicists who are now competing for the same dwindling pot of resources. And so it's really in this moment, in the late 1960s and early 1970s, that you start seeing tensions between different groups of physicists, which previously might have been intellectual rivalries, blossom into something much more. Some deeper resentments start to come to the surface.
Were the changes in the physics community all organizational, or were physicists' perceptions of the natural world and the production of knowledge about the natural world and the quality of that knowledge, were these also changing as well?
Absolutely. Yeah. So on one level, this is about money, it's about funding, and it's about prestige, and it's about influence in powerful organizations. But it's also about how we should think about the world and how we should think about what physics is and what our identity as physicists is. One of the central axes along which this conflict played out was what we would now call reduction versus emergence. Where is it that we find the most important, the most fundamental, the most basic knowledge about the physical world? Some physicists would say you always get a more fundamental explanation. You always get deeper knowledge if you break a phenomena into its component parts and understand what those parts are and what makes them work. So this is the program that was driving high energy physics. This was the program that was driving physicists to want to break up the nucleus and understand its components, understand the pieces that allow it to fit together and make it work. In contrast, people working in solid-state physics were working with phenomena on the scale of the laboratory, on the laboratory bench. They were interested in things like magnetism. They were interested in things like the electrical properties of semiconductors and the mechanical properties of metals. And these are the sorts of things that are relevant to technological development, especially around that time. But many of them didn't want that to be the end of it. They didn't think of themselves as technicians. They didn't think of themselves as people who were only working on improving gadgets. And they thought that the sort of knowledge they were gaining about how matter behaves at these terrestrial scales was just as fundamental and just as intellectually important as the sort of knowledge you gain by breaking matter into its component parts and understanding how the pieces work.
We've touched on some of the topics in your book, and of course there's much more detail in the book. But in the big picture, when you look back at the history of American physics in the 20th century through the perspective of the development of solid-state physics, how does the story seem different from the traditional story?
The traditional story we have of the history of 20th century physics is often one that's told from the perspective of high energy physics and nuclear physics. And this is a story that tends to be quite linear and often goes back quite a long time. So in the congressional hearings over the Superconducting Supercollider and whether or not it should be funded, many high energy physicists got up and told a sort of story about their field, about how physics got to where it was. And they'd often go as far back as ancient Greece. And they'd say, this starts with Thales and Miletus. That's the start of the reductionist program. The understanding of the world for 2,000 years has been about atomism. It's been about breaking apart matter and understanding the components of matter and how they function. And we have pushed that research program as far as we can push it now, and this is the essential next step. In that way of thinking about the development of physics, then 20th century physics looks quite linear. It looks like what the high energy physicist turned historian Abraham Pais called an inward bound narrative, where you start at the beginning of the 20th century, and it's still reasonable to doubt the existence of atoms. The community is really only convinced roundly of the existence of atoms after 1905, when Albert Einstein publishes his paper on Brownian motion. By 1911, you have a concept of the atomic nucleus. By 1913, you have the first iteration of the old quantum theory. By 1925, you have quantum mechanics. 1925 and 1926, you have quantum mechanics. In 1930, you have the neutron. So within this very short span of time at the beginning of the 20th century, you go from it being reasonable to doubt the existence of atoms to a relatively robust understanding, not just of the atom itself, but of the atomic nucleus and how it's put together. After World War II, you can break apart the nucleons. You understand how protons and neutrons are composed in terms of quarks and gluons. And the development of the Standard Model through the 60s and 70s gives you this very coherent picture of how all those pieces work together in a comparatively elegant way. So that story is a relatively linear one. It's about this progressive understanding of the basic components of matter and energy. And it's one that emphasizes a particular type of intellectual accomplishment. It emphasizes that this is the sort of enterprise that's valuable because it gives us basic, enduring, fundamental knowledge about the world. It gives us answers to our deepest questions. And fulfilling those answers is therefore the purpose of physics, and a purpose that it has filled exceptionally well over the past 100 years. So that is it's the basic story that we get from the perspective of nuclear and high energy physics. If you look at it from the perspective of solid state physics, things look a little bit differently. So solid state physics it's also about atoms, but it's about atoms in aggregate. It's about how they work cooperatively, how they arrange themselves into crystal lattices, and what the properties are that emerge when they're arranged in particular ways. And so in that sense, there's no reason that solid-state physics can't claim that it is also the successor of those early 20th century developments. When you're thinking about how electrons move through semiconductors, how the little transistors and integrated circuits in your computers and cell phones work, you're relying on the quantum mechanical principles that were developed in the 1920s and the 1930s. Now, from that perspective, what we see in the 20th century is that actually physics and society are working very closely together. It's driven by the economic concerns of the time. It's driven by the military concerns of the time. It is very closely intertwined with technological development. And that doesn't mean that it's not about fundamental knowledge, but that those things are not quite so decoupled as they seem in the standard story that we get. Another way in which it looks different has to do, again, with the superconducting supercollider. So the cancellation of the SSC was a very emotional moment for a lot of high energy physicists. They felt this is the end of something great. The United States had invested a great deal of resources in the development of this series of particle accelerators, getting ever larger, going to ever higher energies. And high energy physicists saw the SSC as the apotheosis of this research program. So when it was canceled, it represented a sort of betrayal to them. And they were shocked and surprised that the United States government, after having invested in this line of research for so long, would then turn off the tap. If you think about it from the perspective of solid-state physics, that does not seem so unusual, actually. What seems unusual is the fact that the government was ever interested in supporting this line of research to begin with. So, again, recalling that in the early 20th century, there's not much of a physics community of the United States. There's certainly not much centralized government support for physics research. That only emerges after World War II. The culture in the United States is often focused on practical developments. People care very much how the sorts of investments they're making in things like science translate into new technologies, translate into medical developments, translate into economic advantage. From that perspective, solid-state physics seems like a good investment, and it seems very strange that the government would pour millions and sometimes billions of dollars into these large cathedral-esque accelerators on the promise only that they would increase our fundamental knowledge of the natural world. That seems somewhat out of step with the rationales that have been used to support science in other circumstances in American history. So taking this perspective from this discipline that hasn't gotten a lot of attention from historians, but which represents a plurality of physicists from at least the 1960s, we gain a different perspective on what is usual and what is unusual in the development of American physics in the 20th century.
Joe, thank you very much for sharing your work and your perspectives with us.
Thanks for having me. It was a lot of fun.
This has been a podcast from the Consortium for the History of Science, Technology, and Medicine. You can find other podcasts, video lectures, archival spotlights, as well as opportunities to connect with our community of scholars at chstm.org. This podcast is made possible with the generous support of the Pew Charitable Trusts, the Andrew W. Mellon Foundation, and the Rita Allen Foundation.